Hey everyone, thanks for coming and thanks for Martin's introduction. So today I'm gonna present one of a tool I developed like around 2 years ago during the cover competition. It's called like InterLabelGO Plus. It's a scalable and accurate protein function prediction tool using protein language model. And so and this is the outline for today's presentation. So first I will go through the background, like including like what is Dalton and why we need protein function prediction, automatic method for protein function prediction. Then I will go through the architecture and high level detail of of my method. Then I will go through like the data set we use for evaluation and show some result and benchmarking compared with current state of art of method. Then I will have a like small showcase of our web server and standalone package. So finally, the summary of the work. So first, let's move into the background. So so in the field of function annotation, people use Gene Ontology to do this annotation. So what is Gene Ontology? Gene Ontology is provide a standardized structure representation of our current knowledge of biological knowledge. It defines the concept referred as a term or class and that are interconnected through formally established a relationship. So the Galton is designed to be species independent. Hence, the Go allows the annotation of gene product across all the species. And the Go is structured as a graph in which each Galton is a node, and the relationship between this Galton are H. And also Go is hierarchical. So with Charlton being more specific, specialized than their parent term. But unlike strict hierarchical hierarchy, a term may have more than one parent. So example would like right here, this term have two parents. And so the goal is organized in three main aspects. So their molecular function, so which is the specific molecular level activity of the protein, such as binding or catalytic activity, biological process, so which is the process, biological pathway and process that protein are involved in. An example would be like signal transduction or cell division. And last aspect is cellular component, which indicate the location within the cell where the protein perform their function. Example would be like nucleus or mitochondria. So there's no either or part of relation no either relationship across aspect, but there might be some like part of relationship across the aspect. So now we can use Go to annotate a function for protein, but why we need a computational method? So with the advance of like sequencing technology, the number of knowing sequence is growing exponentially, while like manual creation of protein function is usually laboratory intensive, hence are like lag behind. We can see the trend right here. So this shows the number of protein sequence within UniPro KB. So the green line is the UniPro trend data, which mainly consists like unreviewed protein, and red line shows the UniPro sweet spot data protein. As you can see, this red line grows linearly while the green line grows exponentially. So there's a like growing gap, and the data is only up to 2015. So the gap is even larger right now. So there's a need for computational method in an efficient computational method in function annotation. So what is people previously, the most traditional approach is like using template. So here is like an example, a pipeline people were typically used to annotate protein function using template search. So first, we got like a query protein sequence. Then we can employ some searching tools such as Diamond or BLAST to search like a template database. So this is the database or we already know have experimental annotation. Then the tools would give us a report. So here, each table is for like a single GOTAN. So we will have several like heats up to k heats. So then the alignment tools would report a heat score and some other statistic like sequence identity or something. Then we have an indication of whether that protein have that function, have a function. So one would means the heat would have the specific GOTAM, and zero would be like do not have that GOTAM. So then people would usually using a scoring function, and usually we would be like a bit score weighted score to compute the final score for GOTAM prediction. This is like the traditional way to annotate automatically annotate Pony function using template database. So about with advance of deep learning and machine learning, nowadays more methods are starting using like deep learning based method to predict a function from the sequence directly. So here I show some well-known method. So here this here indicate whether you use like a template search, which we just shows before, and this column shows whether you use deep learning component. And with that note, like most of current method are like or at least state of art answer would use compose method, which means you would combine like a prediction from multiple source, which generally would get a better result. So so here we can see there's a lot of different information being used. So most of them are using like a sequence information alone, but some of them are using like a protein-protein interaction network or even literature. So basically they're like doing kind of like a literature mining. Um, and here shows different algorithm. And next I want to point out like the challenge in Go prediction, like at least in the like deep learning framework, because Go so each protein can have a multiple Go annotation. So this is a multi-label classification problem, but it's considerably like more complex than typical multi-label classification. So first, as we discussed before, the Go has a hierarchical structure. So which means the term are like connected by either an partial relationship, forming a like a direct acyclic graph. So as shown right here. So this hierarchical structure lead to a class imbalance because if we have a like a child node present, the its parent node is give it must to present. So and general term hence the general term like binding are heavily represented, while specific term such as like vitamin B6 binding are underrepresented. So here in the graph on on the right displays the log frequency distribution of GOTAN. So this reveal heavily right skewed across three aspects. So like most of so like the common term are like have very high protein being annotated, well like those like very specific term they're large number, but like there less of protein being annotated. Moreover, there are various type of label correlation within the Go annotation. So first, the parent-child hierarchy represent a guaranteed co-occurrence correlation, but there are also some other complex relationship exist as well. Some related terms are frequently being annotated together. For example, here, the vitamin binding and organic cyclic compound binding often co-occur in annotation. And here shows like the conditional probability of one term giving another. And conventional like deep learning based model usually use binary coarse entropy loss. And this would struggle to capture such relationship because the BCE assume independence between terms. So essentially, it is treating Gaussian prediction as a multiple separate binary classification problem. And however, this assumption doesn't align with the intrinsic relationship we observe in the Go annotation. So next, I will introduce our method of InterLabelGO and high-level detail of how we address the issue the challenge we just discussed. So this is the overall pipeline of the InterLabelGO, InterLabelGO Plus. So which is also a composes method that integrates the deep learning based component and alignment based component. So the deep learning based component in InterLabelGO use protein language model for feature extraction. So it will extract last three hidden representation from the protein language model and followed by some simple MLP for the classification. So a key innovation in the InterLabelGO is a novel composite loss function, which we will examine in detail later. So this function addresses the challenge of function class imbalance and explore the complex correlation between protein function. For alignment-based component, we employ diamond to conduct efficient sequence similarity search against the UniProt GLA database, and which leverage curate function annotation. And finally, InterLabelGO Plus combine this component using a sequence identity weighted approach, allowing for adaptive integration of deep learning and alignment-based prediction. So for the novel loss function, so first we employ like protein-centric and goal-centric soft F1 loss. And this would tackle the address the class imbalance issue by balancing precision and recall for both individual protein and goal terms. Such setting would teach model not focus solely on frequent class, and we enhance this by applying information accretion. And I will discuss this concept later. But for basically, this will represent the information carried by each goal term. So next, we incorporate a pairwise rank-based loss, or like ZLPR, proposed by Sun in 2022. Here is the breakdown of the components. So it's fairly simple. So the idea is doing like a pairwise comparison between positive class and negative class. So the goal is we want all the logic of positive class is higher than the negative. However, doing pairwise comparison is computationally expensive because like for example, for the BPO aspect, we have more than 5,000 Galton need to predict. So pairwise comparison would rise around like n squared space and computation required. And here we import like a small trick. So instead of doing like direct pairwise comparison, we can doing like we can insert like a threshold to serve as an agent to compare. So here we just want the like a logic of positive class higher than the threshold, and the logic of the negative class lower than the threshold. So this will achieve like a linear space and computation requirements. And when we set the threshold to like to 0, it will allow us to apply like sigma activation function and to map the logic into the probability. And so the final composite loss is just a simple multiplicative combination of the loss I mentioned above. And so the next is the sequence homology based alignment. We call like alignment KN. So it's fairly straightforward. So we just use diamond to search the prior protein against the template database. And here's the parameter we're using, the ultra sensitive and evaluate of 10. And we will only accept maximum of 500 hits. And prediction score are derived from normalized base score and sequence identity. So like compared to previous method, we just include another like sequence identity to weight for the like scoring function, where the identity can be defined as like the number of identical sequence divided by the maximum of query length or target length. So so to combine the so to more efficiently incorporate the deep learning and alignment-based components, we use a dynamic weighting scheme based on the sequence identity. So this approach allows us to leverage the strengths of both methods in a context-aware manner. So traditional method with just using a like simple like linear combination where there's a like weight given to a specific method, and the weight for another method is just like one minus that previous weight. And that could be the weight could be determined on the validation data set. However, and since like it's only a fixed weight, it will not change depends on like the prior sequence we have. So the weight calculated here is using the mean mean of top 5 sequence identity from the database heat. And we introduced two parameter here, the alpha and k. So the alpha, which represent the minimal weight assigned to the like deep learning component, and k is like a factor determining how rapidly the weight shift from alignment-based method to deep learning-based method as sequence identity decrease. So the idea is like if the sequence identity is very high, we're more confident about like the alignment-based component. Yeah, so so here the alpha and k is also tuned in our validation data set. So for the data set and evaluation, we use like a like a time-based data set. So this is also like follow the standard of CAFA, which is like a community-wise like a function annotation competition. So here we can divide the data set into like three different time point. We call it like T0, T1, and T2. So we use here we can use like all the protein and their annotation before T0 as our training set, and then we can use the like no knowledge protein and limited knowledge protein arise from like T0 to T1 as our validation data set, and arise from T1 to T2 respectively to as our test set. So definition of non-knowledge protein and limited knowledge protein is given here. So for example, if we already have a like if we have a protein that do not have any annotation before, and at the like next time point, it will have some annotation. So this we will consider as like a non-knowledge protein, and limited knowledge protein are like for protein we already have some annotation for at least one aspect. So if we gain new annotation in other aspect, we will use the new aspect as like our evaluation aspect, and then we'll call this as a like limited knowledge protein. And this is like a summary of our training, validation, and testing data set. And here, then I will briefly introduce the evaluation metrics we will use. Before we dive into the like effort measurements, I want to introduce the idea of like information measurement of protein, which we call information accretion, which measure the information gain in annotation in an annotation relative to its ancestor node. So it can score like from 0 and above, where 0 indicate completely redundant information, and a higher value means like more information. And as you can see right here, shows like somewhat like some children might have like lower information accretion compared to its parent. This is because like for example right here, if we have annotation of reproduction, it's very likely we also have the annotation of multicellular organism reproduction. So that's why this skeleton will have like lower like carry lower information. So the formula is given right here. And then we will use F1 measurements, which is a homologic mean of precision and recall, and to measure as our final evaluation metrics. And in the CAFA, they have a slightly different standard, which use like a maximum of F1 score. So basically, instead of like using a predefined threshold like 0.5, you were like loop through like all possible threshold and with a like step set or maybe 0.01 from 0 to 1. So and the maximum of F1 score with doing that process observed during that process would be like the final score. So the score F1 score range from 0 to 1, where 1 indicates perfect prediction, and here is the performance comparison of InterLabelGO compared to other like state-of-art methods in our test set. As you can see, the InterLabelGO perform best in all three aspects, and followed by our like alignment template-based method. And then the combination of these two methods always get a better result compared to like single component. And here we also spend some effort to examine like whether this performance gain is due to like the loss function we designed. So here we have different loss function, binary cross entropy and protein centric F1 score, goal centric F1 score, and also the GLPR. As you can see, the GLPR itself provide a this is example is in the biological process aspect. So as you can see, using the like protein or Go F1 score alone is not doing very good job. It's actually worse than BCE, but the GLPR provide like a huge improvement over BCE. And adding those like protein F1 and Go F1 score to either BCE or DLPR would improve the overall F1 score. So this observation suggests the loss. Yeah. So next is like a case study on us on this unipro protein called is a glutamate receptor interacting protein. So this is the DAG graph showing the biological process skeleton. And so all methods that correctly predict each skeleton are listed below with their icon. So here we can see incorporate the information accretion weighting enable InterLabelGO to predict skeleton with high like information accretion at value, and that other method fail to predict. And there are also some case where like there are a few instances like the deep learning based InterLabelGO miss some term, such as this two term, but alignment based method can be successfully predict them, and a combination of two with able to recover that. And this observation underscore the importance of integrate and like alignment-based method and deep learning-based method to achieve a more comprehensive and accurate Gaussian prediction. And next, I can go through like shortly for our like installation of a standalone package and web server. So so this is the GitHub repository. It will contain every detail, so like environments and how to like retrain the model and how to do the bulk inference. And we also provide a web server for easy access, but the limitation of web server is like it can only accept one query protein at a time. So for batch prediction is preferred to use like to download a standalone package. So here's just like a example. You can input the sample process. The email is optional and the job ID. So here's the example output. So it will shows the original sequence and the template hits and DAG graph for 3 aspect, and the results will contain a TSV file that summarize the Goten prediction. So so by summary, like InterLabelGO Plus use like compose loss function, improve model learning from imbalanced data sets, and it let the model successfully capture some aspect of a Go relationship. And however, crank model doesn't fully leverage Go hierarchical structure. So future work will be like incorporate like hierarchical structure into the loss function or the model architecture. Also, it shows the strength of a composite method. That means we might can add more feature like prediction from protein-protein interaction. And so actually the next step is oh sorry. So actually there's a new round of like Kafka competition is hosting right now. So in this time they actually introduced some like new concept like partial knowledge protein, which are protein previously already have annotation, but like gain new annotation. So they will only use the new annotation as an evaluation, and that result like very challenge to the deep learning model because previously we're using the like previous annotation as a ground truth, so it will penalize the learning process will penalize the model to predict those like unlabeled proteins. So yeah, so we were incorporate some like architecture refinement to help to address that issue in the future. Yeah, all right. So that's all for my presentation. Thank you, and also thanks for Dr. Chenxing Zhang for insightful conversation, and Dr. Lydia Freddolino guidance, and thanks for all members from Lydia Freddolino's lab. Okay. And now I'm open to the questions. Okay.
I really like your presentation, and I have a lot of questions, but maybe I should start with only one. Like Go terms are very generic and context independent. While proteins, for example, are very much context dependent. Their functions are defined by cell state, where all the functions that they do depends on the cell state, cell compartment, cell type, and multiple other things. So my question is, how would you combine all cell dependent functions with something generic as but independent like term?
Oh, so yeah, so that's thanks for the question. So actually that's a really good and that's the challenge point of like how we should train the model, because currently we only use like the UniPro GOA database as like our label for ground truth for doing the training. So at current point we don't have those like cell states label. So that's why like we can only use what information we have, right? So so that's potential drawback of current model. But when talking about like some like state specific, we do observe if we incorporate like for example taxonomy information, there will be like a significant score improvement, which I'm currently implement for like the Papa 6. So yeah. So if we have those kind of data, we can definitely like add those like state as a condition for the for model input, which this would definitely improve the like a model's predictability. But I think the major problem is frankly we just don't have those data. If someone could construct a database that contain those information, we could definitely like take benefit from it. So do you? Okay.
Yeah, I was wondering if you use all the organisms in UniProt, or do you try to like target the organism that's similar to the one that you're annotating?
We're using all organisms that have experimental annotation. So like when we see like the template or like a UniProt GLA database, what we mean is like those terms those protein have been experimentally annotated with some GOTAN. So it will cover like a wide range of species. Yeah.